All right. Salam. Today, I'm going to talk to you about some of our recent works around the topic of anticipating motion and dynamics in multiple levels of abstraction. I think this is going to be a different perspective from the talk that I think Carl gave you guys yesterday. Carl Von Rick's talk on prediction and on predictability. Um, so we know that autonomous agents perceive the world around them and take actions reasoning over visual data in a desirable capability for them is a desirable capability for them that enables them to forecast the next events or actions in videos. Observing the past it's very crucial for them to anticipate what happens next to navigate safely and smoothly. Anticipating the future is a simple yet useful piece of information that helps agents decide what action to take before it is late. Um, I have a lot of videos in my talk. I'm hoping that the video conferencing system allows you to see the videos properly. So if they are choppy and you can't see the videos very well, I'm not sure. Maybe it's the conference system. Anyways, uh, so one way to anticipate the future is to directly predict the pixel values of the future frame. So with this future, it is like predicting the exact feature pixel values. However, this is costly and often very inefficient. This type of visual forecasting defines at the lowest level of abstraction in our abstraction hierarchy. Uh, one of the interesting aspects to learn about is forecasting the future semantics and dynamics between different entities in the scene. This can be achieved if we predict the scene semantic segmentation by observing the past video, defining a second level of abstraction in our levels of abstraction hierarchy. Although forecasting the scene semantics can provide the agent with detailed configuration of scene formation in the future, in some cases, to make decisions, precise trajectories or body part movements are of greater interest. Therefore, prediction of individual trajectories and detailed movement of the body, often referred to as the body pose, are of interest. Detailed trajectory and pose characterize a higher level of abstraction than the previous two that we were talking about. A higher level of abstraction would be predicting the future actions. For example, in this case, intention of the pedestrians, if they want to cross the street or not. The inference can be performed for all of the pedestrians in the scene, and this will define actions or intentions, which designates the highest level in our abstraction hierarchy. So you see that we have 4 levels of abstraction here, from predicting the pixel values, video prediction, until up to intent and action prediction in the future. We've done several works in any of these 4 levels of abstraction, these 4 categories. In a couple of papers, we proposed forecasting visual content in the pixel level, which I'm not going to talk about. I'm going to skip since it may not be of great interest and the publications are rather old. One of our recent works investigated the problem of forecasting the scene semantics by observing the past RGB frames. The goal was to output the most probable future semantic segmentation. We implemented this idea using a student network with three main components: past encoder, 3D convolution and forecasting module, and future decoder. We use supervised forecasting laws to train the model. Our model's capabilities were augmented by a teacher network and a distillation loss, which has access to future RGB frames. One more note, I'm not seeing the chat window or anything. If there is anything, please unmute and let me know. Thank you. Yeah, merci. All right. So in this work, in this paper, we had three different experimental settings of short-term, mid-term, and long-term experiments. Each of them had different input past RGB frames, as shown in this timeline figure. And also, I hope you see my cursor. The target output frames are the same for all of the three settings, as you can see, S19, S19. Since it's very costly to annotate every frame in semantic segmentation tasks, there are few annotated frames. That's why we only evaluated on those and changed the input frames instead. We compared our results with several baselines at the time, such as zero motion, optical flow, a two-stage method that first predicts future RGB frame and then segments it, and the Cornwell STM previously published baseline that was existing at the time of the publication of this work. Our model outperformed all of them using the mean intersection over union evaluation on the Cityscapes dataset for short, mid, and long-term predictions. So let's look at some qualitative results. In this sequence, the car is moving to the right, as you see. Our model is able to predict the more accurate future position of the car, as you can see here, while others often either do not properly predict the position of the car accurately, or even in some cases, this two-stage model completely lost the vehicle, as you can see here. Other examples, the midterm forecasting example, in this sequence, the rider and the bike are moving to the right, and there's one car coming to the left from the behind, moving to the left. Our model is able to correctly predict their future positions and generate better boundaries. There is an interesting phenomenon here that since our model was not given the depth values of the pixels, it doesn't just know which one is going to be in front of the other. As you can see, it's mixing the two, the biker and the car here, which is quite expected, but the results and positions and the direction of movements looked promising. Another example in long-term forecasting example, the ego car is moving forward. As you can see, our model is able to predict the relative motion and future positions of parked cars and generate better boundaries, as you can see, compared to the two best performing previous models. Another example in long-term forecasting, in this sequence, some of the pedestrians are moving left and the others are moving right, moving towards right. Our model correctly identifies and predicts the moving direction of each individual pedestrian, as you can see. For trajectory and post forecasting, that's the third level in our hierarchy. We've completed more works, several works, published some of them published very recently. Let's first start with trajectory forecasting, which is easier. Given a past trajectory, the goal is to predict the future movements. It's even more challenging if there are multiple people in the scene. In this recent work, we only focused on the trajectory forecasting problem, as I talked about. By observing the previous trajectories in the past TP seconds, the goal is to predict the positions in the next TF seconds of all movements. Prior work tackling this task use an auto-regressive ordering on the future time steps. In other words, the joint distribution over the future steps is modeled by first predicting the future point given the past, then predicting the next point given the past and the predicted future point, and so on until the end of the trajectory. But we know that pedestrians are not passive but goal-oriented agents. They have a goal in mind towards a particular direction and exert their will to achieve it. Hence, we proposed to model this idea and follow an endpoint first ordering that better represents the human prior while past planning. This also motivated our title of the paper, which was it's not the journey but the destination. Specifically, we proposed modeling the joint distribution by first modeling the endpoint distribution of the person independently, sampling from the distribution separately for each pedestrian yields to endpoints for the pedestrian in the scene. And finally, we predict all of the future trajectories jointly by conditioning both on the past and sampled endpoints. Our method provides rich multimodal predictions that also respect social constraints. A little bit of more details, we introduced a method called predicted endpoint condition network, PECNET. During training, the past trajectory information is encoded using a past encoder. The ground truth trajectory endpoints are also encoded with an endpoint encoder, the output of which is concatenated with the past trajectory encodings to be used in the subsequent conditional VAE. The concatenated embeddings are then mapped into parameters of the latent space. A latent representation is then sampled from the parameterized distribution and decoded into potential guesses for the future endpoint. Next, these predicted endpoints are re-encoded, forming the predicted destination or endpoint encoding, concatenated with the obtained past trajectory embeddings. They are used as input to our novel social pooling module. We proposed an attention-based pooling operation with a pre-computed social mask and learnable neighborhood weights to effectively merge context across social neighbors. Finally, these embeddings are then jointly decoded with the future prediction module to predict multiple future trajectories, multimodal future trajectories, compliant with both the observed past trajectory and social norms. During inference or testing, since we do not have access to future endpoints, as we were using it during training, denoted by these dashed lines in training, uh, we no longer have those parts active in the model. Specifically, in the past, in the first step, only the past trajectory information is encoded, which forms the conditional information for decoding the sampled latent code in the CVAE decoder. This produces uh, multimodal guesses, a probability distribution for the future endpoint, which then proceeds through the network identically as we described during the training phase here. To evaluate our method, we used two widely used average displacement error ADE and final displacement error FDE metrics. As you can see, they are both unimodal, only comparing one future trajectory with the ground truth, which in general lower is better. Multimodal extension for these values can be also defined by taking the minimum error, unimodal error among a fixed number of predicted guesses for a given past trajectory. And again, this is very common in the previous literature. With these metrics, we benchmark PECNet's performance on the well-studied Stanford drone benchmark. Given a sequence of 8 frames, which is 3.2 seconds long, we aim to predict the pedestrian's position for the future 4.8 seconds, which is 12 frames. We compare against several competitive baselines such as SocialGAN and SOFI. We also compared against the previous state of the art published by Conditional Flow VAE. And furthermore, we compared against concurrent works such as P2, Turl, and SIEM-ARC, which were co-published at the same conference as we published this work in ECCV 2020. All reported results are using 20 samples per trajectory, as is widely used in prior work. Under standardized evaluations, PECnet achieves an ADE error of 9.96 and FDE 15.88, which improves upon the previous state of the art by a significant margin, as you can see here. We repeated the experiments on another benchmark, widely used ETH-UCY benchmark. We follow the leave one scene out evaluation protocol as the prior work, training on the rest of 4 scenes and testing on one of them on the 5th one. We compare against several published, baselines and state of the art in this data set. And again, as you can see, our method on average achieves a really significant performance gain compared to all of the prior work. Here we present qualitative results demonstrating PECNet's rich multimodal predictions, predicting multiple futures. White denotes the past input trajectory, and blue or cyan represents the ground truth future, and red are the PECNet's predictions sampled with different priors. We also visualize PECNet's behavior in case of common pedestrian social interaction modes, such as merging and cut-through. As you can see, different colors are different pedestrians. As it is visible here, the social norms are somehow properly considered when predicting future trajectories. In another work, we looked at predicting both global motion, the trajectory, and detailed local movements, as you can see, the pose movements, body movements, as denoted by pedestrian locomotion forecasting, we called it. Anyways, let's first look at pose forecasting. In regular in prior works in pose forecasting, what they used to be doing is they discard the global motion and only they subtract all of the global motion and map uh, the pose movements on top of each other. As you can see here, only predict the local joint coordinates. But what it does is observing the past. We want to now see how the joint is moving into the future, which, as I said, there are different types of applications for that. In a very first work, what we did was actually we proposed a method called TPRNN, triangular prism RNN, which was a it had a hierarchical structure with multi-scale considerations, which considers the multi-scale nature of human motion in general. We presented a model called TPRNN, as I said. The first level of RNN, the green color in the diagram, takes the velocity, the movements, just the velocities offset from the previous pose as input, and generates after observing all of the past movements, it generates the future, which is again input to the LSTM, continuing into the future and making predictions for each time step. This method was, as I said, triangular prism RNN, and that was the reason for the name, the hierarchical nature of it, and multi-phase nature of that, which has hierarchical, multi-scale, multi-phase data augmentation, and in the velocity space nature. So these are the characteristics of this work. Each of them contributed to gain in results. Testing on the human 3.6 data set, removing each of these aspects of the method somehow increases the error, drops the results. Our method obtained the best results by having the characteristics, all these four characteristics together. Compared to the previous work, especially the previous state of the art, which was called here residual, published in CPR 2017, our model outperforms by a significant margin. Besides, we can see that the performance gains between our model and the previous work become more significant in the long-term predictions. We also compare with residual model, which results are shown in blue. Blue residual, and then ground truths. Our results are in red. You can see the subtle differences in the future prediction and distances of the joints and how they are similar to the ground truths here in this work. So although the previous work that I presented resulted in good performance, it needed a fully supervised setting for training and possibly not enough generalizable to challenging cases. Therefore, what we did was, after that work, we redesigned a method based on imitation learning algorithms to train our model, our prediction agent, under this reinforcement learning formulation. The goal is for the model to learn to generate the expert demonstration given the input state, which is the past sequence of poses. In RL setting, in reinforcement learning settings, or in imitation learning terminology, it means that we generate an action that imitates the expert behavior. This is done by using a policy generator to make sure these actions are in line with the expert behaviors. We use a credit network similar to discriminator used in GANs to generate a reward if action is in line with expert behavior. This is done by policy gradient. We use behavioral cloning for initializing the policy generator network, and then used generative adversarial imitation learning, or GALE, to train the whole network altogether. I don't go into the details of imitation learning and this architecture in general, but you can find more details in the paper if you're interested. Like the previous work, we tested our algorithm on the human 3.6 benchmark, which is a 3D human pose data set mainly used for this purpose, using the mean angular error, MAE. As can be seen in this table, our imitation learning framework again outperforms all of the previous works, including our own previous TPRNN. On average, for all of the different action categories on the data set, our method predicted most accurate fine pose movements in both short-term and long-term predictions, as shown in these two plots. As I said earlier, previous work for pose forecasting often ignore the global motion, and we've done a couple of works in that space too. They remove global motion from the joint coordinates and define the problem to only predict joint coordinates in the local space. In a set of follow-up works, what we did was we predicted the coordinates in global space, which means it can infer both local and global motion components simultaneously, which led to this work, pedestrian locomotion forecasting. Locomotion, we defined it as overall motion of body in space and time, not just trajectory or just the body pose. And our goal was to do pedestrian locomotion forecasting in vehicle-centric views. What we did in a very first work was with raw video. We wanted to also have minimal supervision, because pose data is often very expensive to supervise over. So what we did was we used off-the-shelf pose estimation models like OpenPose, giving us incomplete pose, from which we trained a model to create a complete set of poses, a pose completion framework, which then helped us do a prediction in the global space, only the trajectory and local in parallel. So we did a local and global disentanglement in prediction here, and then integrated, merged the forecasted results to create the full locomotion. The core of our method was a prediction module that can operate both in local and global subproblems, which leverages 3D scene geometry to transform image coordinates to latent representations where the forecasting actually happens. So it encodes the past forecast in the latent space and decodes the future. We did this by proposing a model based on quasi-RNNs, which for the case of pose, the case of trajectory, the position or the trajectory over time was the input, and the decoder's output was future's trajectory. And we use the same architecture for predicting a specific joint, body joint movements. So to evaluate the method, we used this JOD benchmark, the data set, the Joint Attention for Autonomous Driving data set, and used the KDE, key point displacement error, as the metric. Compared to most of the prior work and also state of the art, and our method again obtains significantly better results in terms of this error metric, KDE. So lower is better. Some qualitative results included observing this past. What we did, as I said, we extracted the past pose, as you can see here, and then we made a prediction for the future. As you can see, the future body movements are predicted here. Continuing the same direction, prior work for pose forecasting, as I said, we're ignoring global motion in a set of works. As I showed you the previous previous work, we predict in the global space, but adding to the prior work, the other thing is that most of the previous work ignore the context. They only look at the body movements. So for example, in this example, if you see this past trajectory, the model may think that this subject is this person is walking, so then may predict something like this for the future. While if you have the context, you can see this is a boxing scene. So most probably this person is not walking, and it may be like punching, for example. So the model can somehow infer the punching action and then do such a prediction into the future. But again, one more aspect of the prior work was ignoring social forces. But when we consider the social context of the method, of the work, like knowing that the other person in the scene is actually doing the punching action, person two. So person one that we are interested in their future action, future movement, most probably is actually defending. So the pose predictions should go to the case of how they may look like, the person may look like in the future, as the other person is, how the other person is actually moving. So for this purpose, we proposed another work which was published in IRIS 2020, Socially and Contextually Human Motion and Pose Forecasting. Our model had 4 main modules of encoder: social pooling, spatiotemporal context encoding, and decoder. The encoder module used a gated recurrence unit, or GRU, sequence to sequence scheme to encode the historical past sequence of poses for each individual in the scene. Social pooling module, which produced one shared socially aware feature vector by pooling features across all embeddings. The social operation should be permutation invariant operation, such as pooling, that we propose in this work, and we talked about it before too. Spatiotemporal context encoding used an I3D model to extract the spatiotemporal features from the video, and after a number of MLP layers, it generated the context features. And finally, for each person present in the scene, a feature vector was built by putting together the features specific to that person the social features, and the context features. The decoder module received the concatenated person-specific embeddings, shared social and context features, as you can see here, to produce the predicted pose for each future time step for each single person. The network is trained with a loss function that calculates the prediction error in the global space. For this work, we used the challenging post-track data set, multiple persons, complex scenes, and also a 3D data set of NTU RGBD data set. This data set, we used the actions that involve two people, at least two people, in them for forecasting the future dynamics. For metric, we again used a similar error metric, mean square error. We compare our method with several baselines and prior work methods here. Since the prior work was mainly separated between local and global trajectory predictions, our baselines consist of two components. The first component will define the local forecasting, as you can see here, and the second component here is the global part. Our models are all joint, as you can see here. The first set of methods include simple baselines that do not involve learning, as you can see here. The second batch of baselines are those that involve learning only for local post forecasting, and the learning itself improves results, improves the results. Our model and its ablated versions include joint learning of local and global post forecastings that each improve the results of the forecasting on post-track data set. So if you look at this, some of the qualitative results, which I'm going to move forward. As you can see here, our model, after several frames, which does a joint learning, it provides more accurate prediction of the body movements compared to one of the prior works, which has a state-of-the-art disjoint learning for local and global components. And same for this other example. As you can see again, the model with the disjoint learning framework loses the locations of the individuals in the scene. In a follow-up work, we have moved one step further by modeling different human-human interactions, human-object interactions at different levels over time, using graph attentional networks between humans, and also humans and objects, as you can see here. Not only this, we also propose to continue modeling the interactions in the future. So something mainly ignored by all of the prior work. Lastly, due to partial or full occlusion, or even individuals exiting the scene, the body joints may be invisible in some frames, which can deteriorate training. We propose a training scheme and evaluation metrics aware of invisible joints. This work is to be presented in at ICCV 2021 very soon. So for this work, what we did was I'm going to give a very quick overview of the method. The pose location vectors are put together in this work, encoded by graphs and attention calculated over them. They are then fed into a recurrent encoding, network that encodes the movements over time. We then form a tension graph between the humans. In parallel, an object branch extracts features from the objects present in the scene, enabling us to model human to object interactions with another attention graph. This process yields feature vectors for all of the individuals, encoding their social interactions and interactions with objects as well. We concatenate these with object features and use them to decode future movements in, again, another recurrent network. So how we experiment, for the experiments, we evaluate the method on two new metrics that we defined. Visibility ignored metric, which is basically the previous type of error metrics that people were using, but nobody was considering the invisible joints. But we also have another metric, which is a set distance operation, which is aware of joint visibilities when calculating the error. This time we proposed a benchmark with two challenging data sets of 3D PW with 3D joints and post track, both of them of great challenges. By the way, we are also hosting a challenge and a benchmark in ICCV on this same topic, which you can find on this paper. The URL and links and everything are included in the paper. So in terms of accuracy, all types of prior works, also this our own prior work, number 6. This new method obtains significantly better results than all of the previous works, given that it models the interactions and everything very well. Same story on the other data set, the 2D data set, post-track. For both VIM and VAM metrics, for different metrics that either if there is joint visibility considered or not. Some qualitative results, you can see that since this person is interacting with an object here, for the future prediction, our method tripod was obtaining better results because it was modeling the interaction with the skate, the object, while others, ignoring the object, they cannot properly consider the movements, the future movements. Same story here, because there are many invisible joints. The prior work often randomly just generates some results for the invisible joints, while our method is completely aware of which joints are visible, which are not. Many more qualitative results are present in the paper and the video associated with the paper. I highly recommend, if you're interested, take a look at it. But compared to other very competitive baselines, as you can see, again, because of the complicated movements over time, our method tripod obtains better results, especially when for the cases that there are several invisible joints. So as we go over time, you see how other methods are losing the joint movements, while our method is still generating acceptable results. For the very last part of the talk, the intent prediction, I wanted to very quickly go over this topic of intent prediction. We did a work published in ICRA 2020 we proposed a reasoning pipeline. First, a scene parsing component using instance segmentation of scene elements is used to delineate the objects that may influence pedestrians' intent. When a pedestrian is observed, our model starts reasoning and about the intent by building graph around the pedestrian. We build one graph for each time point and connect corresponding nodes across time. Finally, our model predicts the intent defined as future crossing probability. We first tested our algorithm on JOD data set and also proposed a new data set, a Stanford TRI intent prediction, a steep data set. Here are the results of our method, as you can see, in comparison with methods based on trajectory forecasting, based on past and future poses, and action anticipation and early action prediction methods. As you can see here, our spatiotemporal reasoning framework outperforms all methods by a large margin and obtains an accuracy of nearly 80% for predicting 1 second into the future. When we widen the prediction time horizon, as expected, the accuracy also drops. So 1 second, 2 seconds, or 3 seconds into the future. However, again, our method is obtaining better results as can be seen. Actually, here it's the accuracy exactly into the future and an average over the past 3 seconds. Okay. Some qualitative results I'm trying to load. As you can see here, for this input, our model predicts the future that this person is actually going to cross the street, as you can see, and same story here that because the car is moving very fast, both of these people are stopping at the crossroad. As you can see, they change into red boxes, meaning that they're not intending to cross the street. Same for a longer term prediction. One interesting thing here in this work is the pedestrians coming from the right side in. First, they are red. It means that the model thinks they are not going to cross the street. As they get closer to the curb, the model knows that they want to actually cross the street in the next 30 frames, 1 second, and gives that prediction. As I said, we also presented the data set called the STEEP here, a good large data set with 3 front cameras in 5 dense US cities. And with all 3 cameras, when we build our graphs, still we get very good results. As you can see, again even for 3 seconds in the future, we almost get 81% accuracy, 81% accuracy for predicting into the future. Okay, not to go too much over time, visual forecasting of behaviors at multiple levels of abstraction in a dynamic, realistic environment helps agents make quicker navigational decisions. This requires reasoning over the scene involving all of its components. For instance, an example here for the vehicle and the pedestrians. As you can see, all different levels of hierarchy are very important. Lastly, I would like to thank all my collaborators at Stanford and beyond, and thanks to all of the organizations who funded my research.